So let me share my screen. We have also somebody from Ento joining, as far as I can see. That's good. So sorry about that. Okay, so you should be familiar with this diagram now that we've been sharing with you in all the training sessions we are having. So just a little bit of a recap. You know that the project we are working is divided, is organized in several working packages, and we are providing a cycle of virtual training courses that covers most of those working packages. We started with the DSS view, which is the software designed to manage hydrological data, and it is used for the database implementation, which is the first step needed and useful for both work package 1, 2, and 3. Then we focused on QGIS, that is a kind of a cross-sector, cross-package software. Then we had a session about HMS, the hydrological modeling in work package 1, and today and tomorrow we will focus on HEC RAS, which is the hydraulic model that was used under work package 1. During next weeks, we will also look at HEC RAS and on SWOT. As you can see from this very simple table. So we have now completed three modules, let's say, of this training cycle. Today and tomorrow we are going to focus on HEC RAS, and then we'll have next week SWOT, and the following weeks we will have RAS sim sessions. So I would stop here, other than saying that all those software are kind of connected between each other. So we are basically building a chain of models that are using the results of one as an input for the other. So for example, you know that we started from rainfall to perform hydrological rainfall runoff analysis, and the results of the rainfall runoff analysis becomes an input for the hydraulic model, which is meant to analyze how the flow is routed through the network of Ento area. So we are less people than usual today, so probably could be easier for interactions. The idea is to be as practical as we were for QGIS and HMS. So we are assuming you have downloaded the software and you have installed the software in your computer. If that's not the case, just let us know, because there are some simple exercises that Federica will guide you through that you can do in your own machines, so that we can probably verify if you have any problem, if everything is working. Maybe you can share your screen, or you can simply share some screenshots in case of any problem. So please, let's try to be as interactive as possible. So I will stop here. I will leave the floor to Federica. Maybe before we go on, can you confirm that you have HEC RAS installed in your computer, or at least that some of you have it? Uh, so if any of you has the software installed, please just maybe confirm in the chat here, so that we know that at least some of you is able to follow the exercises online, let's say. Okay. So I think we can actually start. It's now 25 minutes after 9. Uh, okay, so Federica, over to you. Uh, I standing by. Okay.
Ending the RAS training. Share my day. We are an overview.
Yeah, Federica, you are very low. I don't know if it is a matter of just of me, but for me. But anyway, just to let you know that.
Okay. You
Oh,
hear me very well?
I can
Let's
hear you very well
see.
now. Yeah, probably also the others. So
Just a moment. I can try to change my headphones. Maybe improve. Now, can you hear me better?
for me, it's fine now. Hopefully, also
Okay.
for the others.
Okay. Thank you.
Okay, please
So
go on.
yeah, I was saying that today we are seeing an overview of what HEC RAS software is, how is the user interface made, what are all the elements, the tools necessary to make a project. And for today, then we are focusing on the geometry implementation. So we are going to see all the feature, the tools available to make a geometry to perform some simulation. And then we are going to do some exercise. So the first part is, let's say, a little bit more theoretical, and then we will try to apply all the things that we are going to learn with some more practical exercise. So as Paolo said, you will need to have the software already installed in your computer. Well, tomorrow we are going to move and see how to perform some hydraulic analysis, the steady and unsteady flow analysis, but we are going to see in detail what they are. And in the same way, there is first a more theoretical part and then some exercise to apply all the things we learned. So first of all, HEC RAS is it's a software developed by the U.S. Army Corps of Engineers, and the name stands for Hydrologic Engineering Center River Analysis System. So as the name suggests, it is used to perform some river analysis, and this is the page where you can find the software in case you don't have already installed the software. Maybe I can try to show you how to download and install the software in case you don't have already done. So I'm not sure. I did not receive any feedback from you, so we can try to do this install operation together. So if you had any troubles, maybe you can see, but it's quite simple. This is the link of the main page of the HEC page. So let me open a new page on the browser and go to this page. Now there is the 6.7 version, but it's still a beta version. So I suggest you to install the version 6.6. So you just have to download this setup package. I've already downloaded it in my PC. Um, it's not so big, but it may take a little bit of time depending on your internet connection. So if you're downloading now, first let me show another things in the meanwhile. From this page, there is a really useful information. If you move to the documentation page, here you can find different materials, very useful if you are going to use the software. Because, for example, if you go to the documentation homepage, here there are all the manuals, the user manuals, the 2D user manuals, the RAS mapper, and as well as some training guides and tutorials that you can just check online. For example, if you select the user manual, you can see the manual directly here online, subdivided. You can find all the chapter, and you can move and look for any information you are looking for. But maybe even more useful is in the documentation page at the bottom, you can find this HEC RAS PDF documentation. And from here, you can download the manual in a PDF version. So you can look at it whenever you want without any without having an internet connection. So it's, let's say, more easier. For example, if you open this one, you see it's a very complete manual. Just a moment. Okay, it's big. Okay, it's the whole PDF of this manual. It's more than 100 pages, so it covers almost every topic and every aspect of the software. You can easily look for the topic you are looking for from the index, or just searching for with some keyword, and it's pretty useful, I think. Now let's go back to the download of the software. Okay, I already have my setup package here. If you have downloaded it, you just have to execute this file and follow the instruction on the window. So you just have to confirm the process of installation, have to agree the terms and conditions for use. You can select the folder where to save the program. In this case, I just want to keep the default one, the program file folder. And yeah, I want to create a desktop shortcut, so it will be very easy to find the program when the install process is done. And just confirm. It shouldn't take so much. Okay, so it's done. It's pretty easy and fast. Now I can see the shortcut here. It's my 6.6 version. I already have some of the previous one. This is the last one I just installed. Okay, so let's go back to the presentation. So if you haven't installed it yet, as you've seen, it's quite simple. You can try to do it now or maybe during the break, because I think we are going to use the software in the second part of the training of today. But yeah, it's really important if you have the program already installed, so you can try to do the exercise I'm going to show you. And so you will see if everything we see during this morning, it's clear and it's better. So now let's some more people coming. Okay. So HEC RAS is presentation. Okay, it's a software used to perform hydraulic analysis. You can build hydraulic models, and in particular, this software allows the user to perform a monodimensional steady flow calculation, but also one or two-dimensional unsteady flow calculation. You can build the monodimensional unsteady flow calculation. You can build two-dimensional unsteady flow calculation, but you can also create both 1D and 2D model at the same time. You can combine the description of a river with a 1D discretization and maybe all the flooding area with a two-dimensional model. The program allows the user also to perform some sediment transport and mobile bed analysis, as well as some water temperature or water quality modeling. But with, with, with this training, we are focusing only in the 1D flow analysis. So about the monodimensional analysis, there are different kind of flow that can be analyzed. There is the uniform flow, in which you schematize a fixed geometry with a constant flow. Then there is the steady state flow, in which the geometry is variable, but the flow is still fixed in time. And then there is the most general case of flow, which is the unsteady state. In this case, we have a variable geometry and also a flow which is changing with time. With the HEC RAS software, you can perform these two cases, the steady state and the unsteady state. We are going to see both of them during the training. But first, let's see how is the RAS user interface. When you open the software, this is the main window that you will see. Here you can see all the files needed to create a project, because when you create if you want to create a river hydraulics application with this software, you work with projects, and a project is a collection of files that are used to build a model. When you start a new project, you are required to enter a title and a file name for the project, and then all the other data are automatically stored by the user interface using the same name as the project file. Here in this user interface, you can see the different files, so the project, the plan, geometry, steady flow, the unsteady flow. and you can see a description of it on the left side of the menu, while on the right part you can see the related file. So you can see the path where each of these files is located in your computer. So now let's see a little bit more in detail each one of these files, which are necessary to perform to make a project and perform an hydraulic simulation. So the project file is the first file that you are going to create working with the RAS software. The project file is a file which contains all the basic information for the project. It contains the title of the project, the list of all the files used in the project, and the project Unix system. You can see the project Unix system also checking at the right bottom of the menu, and you can always see which are the units that you are using for the selected project. As I said before, all the files created have the same name of the project file. The only difference is the free character extension, which depends on the type of file. So in this case, for example, you can see that this project is called Beavcrack, and yeah, the extension of this kind of file is PRJ. So once the user start a project called Beavcrack, then all the other file will have the same name. For example, as you can see from the plan file, here is description of the file, but here in the location of the file, you can see that this file is called beavcrack and then .p03, but the same name beavcrack is the same for all the files of the plan, geometry, the flow. The plan file, it's the second one you can see in the user interface menu, and this file, the plan files, contain all the information that define the simulation. You can have different plans, and they are identified with and they identify different simulation. They have the extension P01, P02, and so on, because the number corresponds to the order in which they are saved in that project. So you can have multiple plans, and you can recognize them from for sure from the description, but also from this number in the extension. Then there is the geometry file, and the plan files can be created and edited using these two buttons you can see in the toolbar above the menu, while the geometry file can be opened, edited, and created using this button. And geometry files contain all the information defining the geometry of the model, so the river and ridge connectivity, the cross-section, the profiles, any hydraulic structure that can be included in the model. Also, in this case, it is possible to create many geometry inside a single project, and they will have the extension .g01, g02, and so on. The geometry file is actually the file we are focusing today, and it's somehow the most important part of the project, because with the geometry file you schematize the river situation. So it's really important to try to create a geometry file that it's most realistic possible. Okay, if you click the geometry button, this is the geometric data editor that will open, and from here there are many tools and options that can be used to create the river discretization that will be used then for the computation during the analysis. Then the steady flow. The steady flow files contain all the information on the flow and boundary condition necessary to perform a steady flow simulation. So if you remember, the steady flow simulation are simulation in which there is a variable geometry but a fixed flow. So in this file, there will be the flow data as well as the boundary condition and the number of profiles to be computed, because with a single file you can compute a different situation of flow, which is still fixed in time. And it's also possible to create many steady flow files within the same project, and the extension of the steady flow in this case will be the F and then the two numbers uh, saved in order. This is the button for the steady flow, while the next one, is the one for the unsteady flow analysis. The unsteady flow files contain all the information on flow and boundary conditions necessary to perform an unsteady flow simulation. So it's the most general flow simulation in which there is a variable geometry and also a flow changing in time. So the most important information to perform this kind of analysis are the flow hydrograph, the starting flow condition, and all the boundary condition upstream, downstream, and any internal boundary condition. The extension for this kind of file is U and then 01, U02, and so on. Okay, let's move to the geometry, but first just let me know if something is not clear. If you have any kind of question, you can just stop me or write in the chat, raise your hand. It's okay, there is yeah, don't worry and stop me if you have any questions. Oh,
Hello.
yeah,
Yes, I have a question
yes, sure.
for geometry for cross section. Which data I the data I can put in the model? Which data
Which kind of data you need to insert in the
for cross
geometry?
section? Yes, for cross section.
Okay, now we are going to see more in detail everything about the cross section. But yeah, essentially you have to schematize this cross section through a profile and insert a different coefficient like the roughness coefficient. You have to define the banks and so on. But now we are going to see detail because yeah, the schematization of the cross section is the most important part in an hydraulic model because yeah, sure all the results are related to the schematization of the river. So of course, define cross sections which are really good and realistic will assure better results in the hydraulic model.
Yeah, so because I asked like that because there is a model you can when you take cross section using ADC feed and then you attract the data on the model on riverine on the riverine and then you can put it on the model. This is one way. The second way, maybe you can when you take cross section and then you will fix the data, then you will print and put the some models, the some parameters, just like the discharge or velocity, something like that.
Yes, if I
Listen?
can comment on that, Lib,
Yeah.
you raised the, the, the the most important question. As Federica was pointing out, the most important data for a hydraulic model is the geometry of the river, which is usually made through cross section, let's say through topographic survey. Okay,
Mm,
uh, topographic survey can be in the form of a cross section, which
mm,
means like you survey the of the water part with traditional topography, ground topography, and then you use an ADCP, for example,
mm,
to merge soil out of the water with the part of the cross section that is underwater. This is the most usual option. Uh, in case you have a lot of money, you can do some like LiDAR topography for the off water portion, and then maybe yeah you can survey an entire reach again with the bathymetric techniques uh,
mm,
other than just cross section. But other than regardless of the technique that you're using, the main scope is to have a topographic cross-section or a topographic, let's say, reach completely surveyed, both
mm.
out of the water and under the water.
Okay.
So that's very, very important. That's critical. And actually, when we were developing the model of the Nile and its tributaries here, we could rely only on the cross-section surveyed for the Blue Nile. For the other reaches, we did not receive surveyed cross-sections. So we had to make some assumptions and we have to combine like remote sensing data for the portions that are out of the water, and we have to assume a shape for the cross-section under the water. But this is something that you are going to see in a while in the details. That's just to say that yes, cross-section is the most important part, probably for the geometry, and you need a topographic campaign to be completed before you start doing the model. If you don't have this data, you can use some ready off-the-shelf data that have significant limitations. So the results that you will get will be definitely less accurate. Okay, I hope this answers your question.
Thank you.
Okay, if any other questions, I see also there is some people that has entered the meeting room a little bit late. So whatever issue you have, just please interrupt us and make a question. So Federica, please, again, over to you.
Okay, Paolo, thank you. So now we are going to see more in detail how the geometry implementation have to be done. So this is the geometric data editor. You can open from the main menu, and here you can build the model, adding step by step everything is necessary to define a good schematization of the system, which is really important for the implementation of simulations. So the first step is to define the model, just digitizing the river to be simulated. There is this button, the river reach, that allows the user to draw the river here in the main window. And you need to know that each river is defined by a river and a reach. And the boundaries of each reaches can be the beginning or the end of a model, as well as a junction or a split. This is an example of a river just digitalized in the window. And the digitization must be done from upstream toward downstream. And keep in mind that the coordinates have actually no influence on the results of the model. When you digitalize, you can see the coordinates always showed in the right bottom part of the window, but they actually have no influence on the computation, as well as the shape of the reaches has no importance because the model actually can see the curves, but it's really useful for the user to reproduce the correct shape of the river in order to better understand the model he is making. For example, here you can also upload some images as a background, so you can reproduce the correct shape of the river, and you will always be aware of, for example, the location of the cross section, location of any inline structure or any kind of structure and other things present along the river. This is an example of a river made of multiple reaches. So for example, here you can see there is the main river, which is the river A. It is splitted in two parts, the reach one, which is the upper part, and the reach 2, which is the downstream part, because here, where there is this red dot, the junction 1, there is a tributary that joins the main river. So whenever there are two or more streams that come together, there is a junction defined, or also when there is one reach splitting apart. So this is what you need to know about the river and reaches. Then, for each river and reaches, you must define the cross sections. As we said, the cross section represents the most important part of the model because cross section are 3D continuous features that need to be schematized in a single element. And then, based on this cross section, all the computation will be made. So it's important for the user to know all the options allowed by the code for the cross-section definition. So let's start with see how the cross-section data editor is made, you can open this window just clicking on the bottom cross-section from the geometric data editor, and this is what you see. This window will open, and here you can see there is a schematization of the cross-section. On the right side, you can see the plot, so you can see a graphical view of the cross-section, which is immediately clear for the user, while on the left part there is the same plot in a tabular format, so the coordinates, the x and y coordinate, the station elevation, and many other options and values and coefficients that must be set for each cross-section. In particular, each cross-section is identified by a river, the ridge, and the river station. River, ridge, and river station identifiers are used to describe where the cross-section is located in the river station, in the river system. The river station identifier, while it's pretty clear that for example, this cross-section is located in the river named Entella and in the ridge called Entella, because maybe this river can have multiple ridges, so you have to specify in which one is located. Then the river station does not have to be actual river station, like the distance in kilometers or meters at which the cross-section is located on the stream, but it does have to be a numerical value, because the numerical value is used to place the cross-section in appropriate order within a ridge. So the river station is used, oh sorry, just want to, okay, is used to place the cross-section in the order, in the correct order within a ridge. So the river station increases from downstream to upstream. So just looking at the river station, you will be able to understand which is the correct order and see where this cross-section is located. Okay, that's what I said. It's quite useful to use the actual river station, as the distances between the cross-section along the main channel, because in this way it will be much clearer, but it is not necessary every time. It just need to be a numeric value. Okay, so once you have defined the river, the ridge, and the river station, then you have to define the x and y coordinates. You can insert this data in this table, and then the user can see the plot in the graph on the right. And this is the first step to create a cross section. Then it's necessary to set the location of left and right bank. This location will identify the portion of the cross section which is defined, which is considered the main channel, and what is considered left and right overbank area. So in the plot, you would see this red dot that identified the left bank and the right bank. All the portion of the cross section between these two banks is considered as main channel, while the portion on the left of the left banks is considered the leftover bank, called also LOB, while the portion of the cross-section on the right of the right bank is the right overbank. The station of the bank have to be stations that are present in the cross-section. Should select one of the stations that exist in the cross-section. And the definition of main channel bank station is important because then for each cross-section the user have to define the roughness coefficient, and there are 3 different coefficients that can be set for each cross-section. A coefficient for the main channel, one for the left overbank, LOB, and one for the right overbank, ROB. These 3 values can be the same, they can be different. It's up to the user to decide which are the most appropriate value to set. Usually for the channel are used coefficient which are smaller than the overbanks due to the nature of the cross section. It depends on the sediment and riverbed, how it is made. So for sure you can set the 3 different values of roughness coefficient, but then RAS model allow the user also to change the roughness coefficient along the x-coordinate. In this case, you can select from the option menu this option, and you can specify how the roughness coefficient change along the x-coordinate. So you have to raise this adding column in the cross-section editor, and you can specify when the coefficient is changing along the cross-section. So this is a little example just to understand why it is important to set roughness coefficient different from main channel and for the overbanks. This is a very simple cross-section. It is made only of 4 points with a trapezoidal shape, as you can see. And the left bank and right bank are set here at the bottom. This is the left bank. This is the right bank. And in this case, the main channel is considered to be like the straight line at the bottom of the cross section, while the left overbank is the sloped part on the left, and the right overbank is the sloped part on the right. In this case, the Manning values set for this cross section is 0.02 for the main channel, while for the overbanks, both the left and the right, the Manning coefficient is set is 0.05. Okay, this is an example of the rating curves that you can obtain in this case. The red line, so this is a rating curve graph, so you have the conveyance in cubic meter per second on the x-axis, while you have the depth in the y-axis. And as you can see, the red line is the curve that you obtain assuming different coefficient for the main channel and for the overbanks. So the value you can see here in the table, 0.05 for the leftover bank, 0.02 for the main channel, and again 0.05 for the right overbank. While if you set the coefficient of 0.02 for all the cross-section, both main channel and overbanks, you obtain the blue line. So this is quite different in the computation, and so user should keep in mind what coefficient the user have to pay attention to the roughness coefficient that is set for the each cross section. Another option is that the roughness can be variable according to the water level or the flux. In this case, from the option menu, the user can select this option of vertical variation, and this window will open. Here, the user can specify the water level. Actually, the vertical variation can be based on water surface or on flow. If you select the water surface, the first column will be the water level, otherwise it will be the flow. So in this column, you set the values that could be considered for changing the roughness, while the station essentially with this option, there is a change both vertically and horizontally. So with the column, you can set which are the values that make a vertical variation, while with the station, so the rows highlighted in green, you can set how the roughness coefficient changes horizontally. While in the middle, all the itself in the middle, you set the roughness coefficient, and the program will automatically use the correct one. It can interpolate between the values in case there is not the exact values. Then another important thing in the cross section is the downstream reach length. It's the distance of the selected cross section from the downstream cross section. As you can see, there are three distances, one for the main channel, one for the left overbank, and one for the right overbank. Now maybe you can wonder why there are three distances between the cross section in a model which is only monodimensional. And now I try to answer this question. So let's take an example. This is a river. We have cross-section A, cross-section B, and cross-section C. The distances measured along the main channel would be this one, the D1 and the D2, the blue curve you can see in the image. But what about the distances along the overbanks? For example, the distance of the right overbank, you can imagine like the water flowing somehow in this way. So the distance would be something like this. Now keep in mind that as I said before, the shape of the river actually has no influence for the model, because HEC RAS software always consider the water to have to be in a perpendicular direction to the cross section. So the schematization would be like this. We have a cross section A, B, and C, and this is the distance schematized from D1 is the distance from cross section A to cross section B, and D2 is the distance between cross section B and C, and this distance is considered to be straight and perpendicular to the cross section. So if you consider the cross section like this, the distances of the overbank would be this. But this schematization is not correct because, as we can see, the distance of the right overbank is actually much smaller. The water is not going to do all this path flowing from the cross section A to the cross section B, and then from cross section B to cross section C. So if you set only one distance, both for the channel and for the overbanks, there will be two errors. You will overestimate the volume of the water flowing in your river, and you will overestimate the right bank path. So the program allows the user to specify 3 different lengths in order to remove this kind of error. This is a particular case if the river is quite straight and there are no such bending curves. Maybe using the same distance is okay. But yeah, keep in mind that in cases like this, it's important to specify 3 different lengths because yeah, this should be like the correct distances to set for the right overbank. Yeah, as I said, the flux is always perpendicular to the cross section. So this is important. But this is still a monodimensional model. So then in the computation, the software uses only one distance, which is an average, a weighted average of the distances between the channel, the left overbank, the right overbank, weighted with the flow that that occur in each part of the cross section. Okay, so this is associating different reach lengths was one of the options to useful to simulate some particular layouts that can be present in the river schematization. Then there are other options that RAS offer to the user, which is the possibility to insert some ineffective flow area, to insert some levee or blockade obstruction. These are some tools that the user can use to make a more realistic schematization of the river. And now we can see them more in detail. But first, I would like to stop a little bit and ask you if everything is clear or if there are any questions of which we have seen until now. Okay, let me see also in the chat if something. Okay. Okay, if everything is clear and there is no question, I can go on. And we can see these free tools available in making the geometry. So the first one is the ineffective flow areas. This option.
Yeah, Federica, sorry, we have a
Yes.
question from
Yeah.
our colleague.
Yes.
See the chat.
I didn't see it.
So Luki is asking.
Okay, sorry. What is the right bank path on measuring cross-section? Okay, so let's go back in. Okay, what is the right bank path? In this case, you can assume a distance like this. You should like consider every specific situation and imagine what happened in this specific situation, or maybe yes, look at what really happens in this place, and you can set a distance which is the most realistic as possible. You can also say try to fix a value of the distance to a simulation, and then looking also at the results of the computations, decide if this assumption is correct or not. Maybe try to reduce more the distance or increase a little bit. But let's say that looking, for example, at this topographic image in the background, you can be able to estimate a possible distance of the right bank. Okay, let me know if I answered your question, if I was clear enough, or if you have any other questions. Okay, you're welcome. If there aren't any other questions. Okay, I go on with this. Okay, so the ineffective flow area is an option that allows the user to define some areas of the cross-section that will contain water that is not actually moving. So, for example, these flow areas are often used to describe portion of cross-section in which the water will pond, but the velocity of the water is zero or really close to zero. So from the option menu, the user can select this tool, and you have to set the location, so the coordinates, the left and the right position of the ineffective flow area, setting a station and an elevation. There is the option to make this ineffective flow area as permanent, because when you set a station and elevation, if the water surface level goes above the elevation you set, the ineffective flow area will automatically disappear, and the water included in that portion of the cross-section will start flowing and contributing to the conveyed flow. While if the user set the permanent condition, this means that even when the water level is higher, the ineffective flow area is still considered from the model. And when you set an effective flow area for a cross-section, you will see this in the note box that is at the bottom part of the cross-section data editor. Here is an example of when this tool can be used. For example, it can be really useful to schematize the portion of the area near the bridges where there are some abrupt expansions or contraction in the flux, and in that area the water isn't really flowing. So for example, let's see at this picture. This is a river where the flow goes from north to south, and this cross-section is is this one. Here there is a bridge, and this is the cross-section just upstream of the bridge. So as you can see, this part is the main channel. So it's this part in the map. There is a schematization of the bridge, and here on the right banks, right hover banks, which is this portion, the map, an ineffective flow area has been set. When you set the ineffective flow area, you can see from the plot with this green dashed line. So this part on the right of the bridge is set as ineffective flow area, and same things that be done for the cross section downstream. In this case, the graph on the left correspond to this cross section, which is located downstream of the bridge, and in this case, this portion of the right over banks have been set to be an ineffective flow area. So as you can see, the blue color, which represents the portion in the cross section where the water flows, it's not colored this part because this is meant to be like still water. And okay, another case where this ineffective flow area can be useful is for some overbank zones that do not contribute to the actual flow. Like if there is a portion in the overbanks where the water will create like a pool, and the water is still here with a velocity really close to zero. This tool is like an assumption that then must be checked with the results after the simulation run. So these are all implementation that the user can set in the model, but then since they are all assumption and schematization, all these assumptions must be checked after a simulation. In this case, the ineffective flow area decrease the area in terms of energy equation, but they do not increase the wet perimeters. This means that along the ineffective flow area, there will not be any friction. Okay, the levee is another tools offered by the RAS Geometry Maker, and you can set the levee for each cross section. When you set the levee, no water can go to the left of the left levee station or to the right of the right levee station until the water surface level goes above the levee elevations. Once the water level gets higher than the levee, then the excluded area is immediately included in the calculations, and the water also flow in this portion of the cross section. The levee option is generally used in the steady state simulation, where you obtain the profile along the river. In this case, you can see if the water surface level is higher or lower than the levee. If the water surface is higher, this means that that the water overflow the levee, and this can be a problem if you are simulating some unsteady flow simulation, because in the unsteady flow analysis, the levee can be used only if they are never passed, because the overcoming of levee causes a shock in the solution, and you probably will get an error that will stop the simulation. So let's see an example in a cross section. The levee can be added from the option menu. You can select the levee option, and you have to set the station elevation for the left levee. For the right levee, you can insert only one of them, both of them, depending on the topographic situation. Once you set the station and the elevation, you will see this pink object in the plot, and you will also have a note in the box note at the bottom. In this case, the levee are pretty useful for this cross section because, as you can see, the water surface level has this elevation, but since you have set a levee, the portion of the cross section on the left, even if it has some elevation which are lower than the water surface level, it's not filled with water. This means that the water can flow only here in the main channel, and that the water will go to the left overbank only if the water surface level goes over this elevation. Otherwise, if you do not set a levee, the program is not able to understand if these two portions of the cross section are connected or not, and it will automatically compute in a calculation the area also of this part. So if the water surface is very low, for example, it's like this, you will have the water flowing only in this part, in this portion. But if the water surface goes up, I can try to use this one. Okay. So if the water surface, if you have no levee and the water surface is lower like this, you will have flow only in this area. But as the water surface goes up, the program will automatically compute also the area of this portion. If you set a levee, this is not going to happen. Okay, the levee can be used to schematize dikes, banks, or vertical walls. So let's have an example. Here we have this river where there is a wall which is drawn with this blue line. So in this case, the cross section here have a wall here in the middle, just on the right hover banks. This means that the water cannot go in the right hover bank until the water surface goes up of the wall height. And so in this case, the use of a levee is really suggested, because otherwise the water will flow also in all this portion, which is not a realistic schematization of what happened in this river. The levee do not take into account the external area until the water level passes their height, but they do add wet perimeter until they're active. This means that during the computation, in this portion of the wall, there will be friction. The model will calculate the friction also on this vertical portion of the wall.
Yes, Federica, there is another question from Lieb.
Okay.
Not sure I can understand it.
Mean the river out bricks. Okay, I'm not sure what are you asking, Lib. Maybe you can also turn on your microphone if you want, and maybe try to understand better what are you asking.
Yes. Hello?
Hello, Lib.
Yes, I mean it's mean the outbreaks of the river, because when you do a rating curve of river, there is many breaks out.
Maybe if you mean if you can if the levee can be used for a simulation of breaks in the river, do you mean?
Yes.
No, in this case, no. There is another option that allow the user to simulate breaks along the river, but no, in this case, it's just a threshold, let's say, to prevent the water from flowing like in the overbanks, but it's not actually a break along the river. Did I answer your question, or did you still have any doubts?
Yes, it is okay. If I want to know, it is break or different.
Because to simulate breach in the river, there is another option that allows the user to schematize like a lateral structure, and you can set a threshold on which then the water will flow outside the river, and maybe if you have also a B-dimensional schematization of the area outside the river. You can also check the flooded area. But yeah, no, in this case, the levee is only an option to set the portion of the cross section in which the water will flow and prevent, like in this example of this cross section, is to prevent that the water flow automatically also in this portion of the cross section, which is not connected to the main one, and it wouldn't be realistic to have the water flowing both here and here. Okay, if it's clear, I can go on with the next option available in the geometry. Okay, which is the blocked obstruction. The obstructions is an option that allow the user to define some areas of the cross section that will be permanently blocked out. This means that in these specified areas, the water will never flow. The block obstruction can be added from the option menu, selecting the obstruction tools. And also in this case, you have to set the station and elevation. In this case, since this is an area, you should okay, you should set a starting elevation, an end elevation. No, sorry, a start station and an end station, and the elevation of this obstruction. You can set the one single obstruction, or in this case, there are multiple blocks. So as you can see from the plot, there are 4 blocks, and in fact, you can see 4 different rows, each row corresponding to one of the blocks. As you can see, like the first one has a starting station of 19, an ending station of 33, which are the x coordinates here, and this fixed elevation of 14 meters. The same for the other 3. When you set these options as the previous option, you will have a note in this cross section that warns the user that this option has been turned on for this cross section. The blocked obstruction are used to simulate obstacles like buildings that maybe are present along the cross section, because you know that for sure in this portion of the cross section there will be not any flow. About the calculation, the blocked obstruction take out the occupied area and add the wet perimeter. This means that the friction along this perimeter are computed during the simulations. And this kind of tool don't stop the water beyond their boundaries. So let's say in this cross section, even if there is this block obstruction, the water is free to flow both on the left side and on the right side, which is the main difference from the levee, for example, that stops and prevent the water flowing from is left side or right side, depending on if it's the left levee or right levee. Okay, another suggestion that can be given to the user is the one to use the section that are not straight lines, because as I said also before, the flux is always considered to be perpendicular to the cross section. So in case you have to schematize a curve, it's useful to use cross section that are not a straight line. So in this case, as you can see, there is the part of cross section along the main channel, which is always perpendicular to the river schematization. And bending the cross section in the overbank will create also a distance of the right bank and overbank, which is more similar to the real one. But also in this case, this is only an assumption of the flow path, and then you must check with the results after the simulation run. Okay, let's move to another. Okay, the junction. I already said a little bit about the junction. The junction are defined as location where two or more streams come together or slip apart. Like in this case, there is this main ridge that is splitted here with a junction because there is a tributary river that come together, this one. So the main river is split into two ridges, the ridge upstream and the ridge downstream. When you insert a junction, the user must specify the junction length, which is the distance between the two ridges to the cross section downstream. So in this case, we have the main ridge, and we have to specify the distances between the cross section downstream the junction and the first cross section upstream the junction, which is this blue distance. Same thing also for the ridge 2. We have to specify the distance between the cross section immediately downstream of the junction and the first cross section upstream the junction, because the software automatically set a distance of the junction, but which is not correct, and the user must change it according to the real situation. For the junction, then there are two computation modes that can be used: the energy balance or the momentum balance. In case you use the momentum balance, you also have to specify the angles between the ridges, because with the momentum balance, the computation is done considering the forces, the vector, so also the angles are necessary for the computation. Okay, and now let's move to the last tools that we are going to see about the geometry for today, which are the inline structures. The inline structures allow the user to schematize some inline dams, weirs, or gated structure that can be present in the river basin. The inline structure can be added just clicking on this inline structure button, and this is the window that will open. From here, the user can specify all the characteristic of this inline structure, starting from first of all, let's say that like the cross section, these inline structure are identified by river, reach, and river station, which are information necessary to define where these inline structure are located within the river and reach. Then it's necessary to specify the wear and embankment characteristics. Essentially, here the user have to set a distance, which is the distance between the upstream side of the weir and the cross section immediately upstream of the structure. This is a distance entered in meter if using the metric system. The width is the width measured at the top of the embankment, while the wear coefficient is a coefficient used for the standard weight equation. So it's a coefficient used in the computation. In the table, the user have to answer the so here you can define the geometry of the weir and the embankment. This information is are the station and elevation of the top of the embankment, and it describes essentially the shape of this inline structure. In case there are also with the description of the weir embankment, you essentially uncontrolled overflow weirs. But if there are also some gated spillways, this is optional, but if it's the case, the user can enter a physical description of the gates as well as the required coefficient, because you can select different gate type, and for each of them there are different coefficient that must be set for the computation. Like in this case, this inline structure is made of different gates. Here you can see there is gate group. In this case, we are looking at the gate group number 2, which is made of 9 openings with these physical characteristics. So the 9 openings are essentially these 9 white windows, which are all characterized by a height of 6.5 meters and a width of 30, while in this table, the user has set their centerline station to the position inside of cross-section. Then probably there will be the gate number 1, which is the description of these other 2 gates. If any gates are present in the unsteady flow data simulation, a boundary condition is required to describe how this inline structure works. But we are going to see more in detail about the boundary condition tomorrow. So for today, we have seen most of the useful characteristic about the geometry, and then after the break, we are going to do a little 2 exercises about what we have seen until now. If you have any question, please free to ask. And then I just want to make sure that you have the HEC RAS program installed in your computer, because in the second part of the training of today, so after the lunch break, we are going to do this exercise, and you need to have the software installed, as well as the training material that we shared with you a couple of days ago. And in that folder that we shared, you can find this folder. So, for example, in exercise 1, there is a couple of files that you need to do the exercise, as well like in exercise 2 and so on. So if you haven't downloaded yet this training material, please try to download and make sure that you have all these files available, so you can try to do the exercise during the next session.
Yes, Federica, thanks a lot. So just to summarize, also for those who are able to join a little bit later than when we started. So you basically we basically started with the general description of all the tools that we are going through in this cycle of virtual trainings. HEC is one of them. HEC RAS is one of them, and it's mainly devoted to the calculation of water flow and levels inside within a river network. So in this perspective, you can imagine how the hydrological model, the HMS, that you have been following the training a few days ago. The HMS is calculating runoff starting from rainfall, and it provides a time series or results, let's say, in terms of flow. That flow can be used as an input for an HEC RAS model that calculates in detail the water level and the flow in each point of the network. Clearly, what is of great importance is the availability of river cross sections, which not always is so easy. But that's the main data that you need while implementing a RAS model. So Federica focused mainly on the geometry implementation in this part. And so I guess that the exercise that you will see after the break will focus on that. Again, it is really important that you have the model installed in your computer, as well as you have access to the shell folder, as Federica was already highlighting. Again, feel free to interrupt, to raise your hand whenever. I see there is Luki is asking to give more explanation on gates. Federica, I don't know if it's something that you might want to go through now in the remaining couple of minutes, or if we should do it later.
Okay, I can try to explain a little bit now. When you insert a gate in a inline structure in the geometry, you can like, let me share again. You can describe the physical, you can make a physical description of the gate, and then you can also fix some rules about how this gate works during the simulation. So for example, you can fix a threshold, maybe in the flow. And so, for example, the gate is closed until the flow reaches a a threshold, and then when for example, the flow goes up this value, the gate will be considered open, for example. This is an example of a rule that can be set during the simulation. There are many others, and the user is quite free to also write its own rules in order to describe the real functioning of this kind of structure present in the river. Maybe it was, yeah, did I answer enough, or do you want to have more precise details? Because yeah, it's quite an advanced tool that can be used, so it's really
Yeah, maybe Federica, yeah, there are some basic functionalities and some advanced functionalities. So
yeah,
I think
exactly.
your exercises will now focus on basic functionalities. If we have additional time, definitely we can also look at some advanced functionalities in some example application, which is easier so to get the concept, I guess. So maybe if we have time tomorrow, that could be another option that we can see. So suggest that now we make our break and we adjourn in 1 hour. So at 2 p.m. your time. Yeah, please be sure you have HEC RAS installed on your machine so that we can start working on that. Okay, so let's stop here and let's meet us again. Let's meet again here in 1 hour. Okay, see you in a while then.